Alright children, so in continuation with the previous 4-5 videos that I had posted on the first chapter of physics, that is force, this is the last video of the chapter where I'll be explaining you some of the important, some of the last topics in the chapter, but yet they are important. So you see we have uniform linear motion and uniform circular motion in comparison. Okay, so as long as we do a comparative study, it will be easier for us to understand what uniform circular motion is. So basically this will be our focus, uniform circular motion. But to understand this clearly, we need to first understand what uniform linear motion is. As the word suggests, linear motion is rectilinear motion or motion in a straight line. So here I have taken a particular example where there is a ball which is moving at a speed of v meter per second. Okay, so you see we already know the difference between speed and velocity. Speed is a scalar quantity, so it will only have magnitude, the value. Okay, whereas velocity is also having direction as one of its criteria. Okay, so if we have a look at the motion of this particular ball, it is moving, let's say, at a speed of v meters per second. So what we can say over here is that the magnitude of the speed is constant. So the value of the speed with which it is moving forward is constant. Okay, so that is one aspect. Now have a look at the direction aspect. Direction of the motion is also same. How can we say that? Because it is always moving to the right hand side. Okay, it is always moving in a straight line in a particular fixed direction. So the direction also is not changing. Okay, so both these aspects, the speed, the value of the speed as well as the direction of the motion, they both are constant. Okay, so basically as a conclusion, what we can conclude is that this sort of a particular this sort of a motion can be called as a uniform velocity motion. So neither is the value of the speed changing nor is the velocity changing, because velocity depends upon two things: the speed or the value of the speed and the direction, okay, which both of which are constant in this particular case. So we can say that this motion is a uniform velocity motion. Okay, now uniform means same and velocity you already understand. Now have a look at this particular case, uniform circular motion. Okay, so obviously circular means moving in a circle and uniform means fixed or same. So now see, let us check what all things are same over here. Now here also for convenience, like in this example I have taken the speed or the magnitude of the velocity to be v meters per second. Okay, so v meter per second here also, v meter per second here also, v meter per second here also. Throughout the motion the value or the magnitude of the speed is constant. So I have written over here speed is equal to constant. Okay, but can we say the same thing for the direction also? No, because direction, you see, I have drawn the tangential directions of motion at different instances throughout the circular motion. You can see that this is the direction of the motion when the ball is over here, whereas when it reaches over here, the direction of motion is again tangential, so it is in this direction, this direction, this direction, and so on and so forth. Okay, so you can see that in this particular type of a motion, which is a circular motion, although the speed value is same throughout, but the direction changes continuously. Okay, in fact at every instant the direction will be same. I can't draw so many instances, so I have shown you these 4 or 5 places where the ball is. So the direction this time becomes variable. Okay, so obviously once again when we talk about velocity, when we talk in terms of velocity, we will consider both things, the speed, the value, as well as the direction. So although the speed is constant, the direction is changing, therefore we can say that this is not a uniform velocity motion, or it is a non-uniform velocity motion. Okay, the reason why it is non-uniform is because the direction changes continuously. Okay, so can we say that uniform circular motion is an accelerated motion? Very much so. So that is why I have written in the conclusion also, uniform circular motion due to the change in the direction of motion continuously is also called as accelerated motion or non-uniform velocity motion. Okay, so as long as the velocity keeps on changing, there will be some acceleration, as we have already studied. If you remember, the acceleration formula was v minus u upon t. Acceleration as well as both the velocity, these are vector quantities. Okay, so as long there is a change in the velocity taking place, there will always be an acceleration present. Okay, so there is an acceleration present over here, there is no acceleration present over here. Okay, so we can say that uniform circular motion is an accelerated motion. Okay, so the last topic that we have come to is the centripetal and the centrifugal forces. These two forces is a part of the fourth chapter. This is the last topic that we'll be studying. Okay, so let us start with the centripetal force. I have written the meaning also. If you read in the book the entire centripetal force, the reason why this force comes into play, the particular situations in which this force comes into play, everything is given. So in brief, I'll just help you explain what it is. Centripetal force is the center seeking force. Okay, a force that is always seeking the center. Okay, so when we talk of center, we talk of a circular motion. Okay, so let us once again have a look at this circular motion that is going on. Okay, so supposing that the motion has started from here, this is the ball or the body that is undergoing this circular motion. As you can see in this diagram, I'll draw some arrows. Okay, so the body over here is moving in this tangential direction. Okay, so it has a tendency to move in this tangential direction, but the question is, does it really continue to move in this direction after some time? The answer is no. Why? Because after some time we notice that the body of the ball undergoes a slight change in the direction. Okay, a slight change in the direction of the motion, and supposing it reaches over here. Now the direction of the velocity is once again tangential. Okay, but does the ball really move in that direction? Once again no. After some time we realize that this ball again takes a turn in this particular direction. Okay, and according to the Newton's laws of motion, we already understand that no body will change its state, whether that state is of rest or that state is of motion, unless and until there is a external influence which is acting on the body. So if this body was to move in this tangential direction, what made it to take a turn? Okay, so there must have been something pulling it towards the inside or towards the center of this circular motion. Similarly, when the body reached over here, it had a tendency to move away in a tangential direction, but did it really go in that direction? No, somebody pulled it back again. Okay, so again there is a force that is acting on the body again towards the center, trying to bring the ball towards the center. Okay, once again you see, now this is the third position where the ball has or the body has reached during its circular motion. So at this instant it has a tendency to once again move in the tangential direction, but does it go away in that direction? No, somebody again pulls it back towards the center. Similarly over here, so you see this force that is constantly acting on this body, not allowing it to go away in a tangential direction, but always remaining in the circular motion. And if you can see, the direction of this force is always towards the center, which is the center seeking force, or also known as the centripetal force. Okay, so this force F that you see over here, I'll label this over here as force F. This force is the centripetal force that is acting. Once again, you can analyze this motion in terms of the value of the speed and the direction. The speed value is constant, but the direction is changing continuously. So this is also an accelerated motion. Now, what are the practical examples that we have for this particular motion? I have listed a couple of them over here. In the book you will find many more. Electrons moving around the nucleus in their respective orbits. So why do they continue to move in their orbits? Why don't they fly off in a tangential direction? Because the nucleus being positively charged and the electrons being negatively charged, they are being pulled towards the center because of electrostatic forces of attraction. So that force in this particular case is acting as the centripetal force. Okay. Similarly, in case of planets revolving around the sun in their respective orbits, what is the force that is actually causing all the planets not to fly off in the tangential direction but to remain in their orbits? Is the gravitational force of attraction between the sun and the planets. Okay, so I hope you have got a fair bit of an idea of what the centripetal force is. Now moving on to the centrifugal force, I have drawn a particular diagram over here which will help me in explaining the centrifugal force, and so that you also understand it well. Okay, so let's now start with the centrifugal force. Now I'll first explain the scenario, okay, and then I'll help you explain what centrifugal force actually is. Now this is a rough diagram of a merry-go-round, a wooden merry-go-round which is lying horizontally on the ground, okay, and this is the center pivoted position, and you have a thread or a string which is attached to a ball over here. Let's say the original position of the ball over here is B, and then there is a person A. There's a person standing at this particular point over here. Now suppose the merry-go-round is started, okay, so it starts the circular motion in this particular direction of the arrow, okay, and after it has gone through let's say a couple of rotations, okay, we will find that this particular string with which the ball is attached, it becomes tight, it becomes taut, okay. So we can see that along with the merry-go-round, this man standing over here also starts undergoing this kind of a rotational motion, as well as this ball which also moves around in the circular motion. Now how do we explain the centrifugal force? Now let us first let me read the definition of the centrifugal force that is given in the book. It says that centrifugal force is a force which is assumed by an observer moving with the body, okay. So where is the observer in this particular case? This man is the observer over here, and as you can see, he is also moving with the body, okay, because the merry-go-round is undergoing rotation. So the person who is standing over here is also undergoing that same rotation, and the ball over here which is attached to the center is also undergoing rotation, okay. So an observer, the force which is assumed by the observer, this observer moving with the body to act on the body in a direction away from the center of the path, okay. So you see, this is the center, okay. So the centrifugal force is directed away from the center. Now how does this person experience it? Okay, please remember that the definition says that centrifugal force is a force assumed by the observer. So it's not a real force, it's not an actual force, but it is only assumed by an observer standing over here who is also undergoing rotation. Now how does he explain this particular force or the centrifugal force? He stands over here, okay. Now the moment, suppose this is the first situation in which the ball is over here, okay, and we cut the string over here, okay. So this particular point we have cut the string, so there is no more tension in the string. So will this ball continue to go round and round? No. The moment this thread is cut or the string is cut, the ball becomes free to move. Now where does it move? How does it move? It moves along tangentially like this, okay. So the ball was over here in the first instance, okay. So now please remember that after the string has been cut, this merry-go-round is still undergoing rotation, and the man standing on the merry-go-round is still undergoing rotation. The only thing that has gone free is the ball, okay. So in the first situation, if you notice over here, A1 is the position of the man, B1 was the position of the ball, and D1 was the distance between the ball and the man, okay. After some time, what you observe is the person, after changing his position from A1, he reaches over here to A2. Why? Because the person is still standing on the merry-go-round which is undergoing rotation, okay. So from A1 he comes to a position A2. But where does the ball go? Now this particular person observes that the ball has moved to a second position B2 over here. Now if you observe carefully from the diagram, you will find that the distance D2 between the ball and the person, whereas the distance D1 between the ball and the person in the first position and the distance in the second case becomes different, okay. So D2 he observes that D2 is slightly more now in comparison to D1, which means that the ball has moved slightly away, radially outwards. Okay, so this direction, if you observe, this direction is radially outwards, means away from the center. Okay, away from the center. Then again, after some more time, the person standing over here at position A2 moves to a third position A3 because he is still undergoing rotation. The merry-go-round is rotating, but the ball is free to move. So in the third position, from the third position A3, he observes that the ball has moved on further away, radially outwards. Okay, so once again, if I draw the arrow over here, so this time the distance D3 between the man and the ball has increased even further. Okay, and the direction of movement of the ball is once again radially outwards. Similarly, in the fourth position, you can see over here the ball has reached a position B4, whereas the person has reached the position A4. So D4 has increased even more, and once again the motion of the ball is radially outward. So in order to explain such a kind of a motion of the ball, this person over here has to assume that there is a force, there is a fictitious force or a pseudo force or an imaginary force which is acting on the ball. And what is the unique property of this force? The property of this force is to take the body away, radially outwards, away from the center. Okay, so in this aspect you can say that centrifugal force and the centripetal force, they are exact opposite of each other. Centripetal force on one hand tries to bring the body, tries to act on the body towards the center, trying to bring it towards the center always, whereas centrifugal force is always acting radially away from the center. Okay, so it is because this force is assumed by the observer to explain such a kind of a motion, therefore we have different names for the centrifugal force. It is called fictitious force or imaginary force or pseudo force. Okay, now the last important point before we end this chapter is to note, this is sometimes, even I think in the current year this has been asked, centrifugal force is not the force of reaction of the centripetal force, although it would be common for a person to make a mistake wherein he says that centripetal and centrifugal forces are actions and reactions. No, they are not. Centrifugal force although acts away and centripetal force acts towards the center, but they are not you cannot say that centrifugal force is the force of reaction. It is not the force of reaction, because action and reactions, they act on different bodies. Okay, action and reaction, they do not act on the same body, whereas you can see the same centripetal force and the same centrifugal force, they are acting on the same body, so they cannot. If they are the reactionary, if the centrifugal force is the reactionary force, it cannot act on the same body. So if somebody asks you a question, is centrifugal force a force of reaction of centripetal force, the answer would be no. Okay, so just go through this in the book. You will find a detailed explanation of this example is given in the book. So my explanation, I hope it helps you to understand what is written in detail. Okay, so with this we come to an end of this chapter. I hope you will all revise and solve as many numericals as you can. Okay, thank you.